Welcome to video 8.3 over heat change calculations. In this video, you're going to understand the concepts and relationships between heat and temperature. In this video, I'm also going to show you how to calculate the change in heat of a chemical, including those with a phase change. Like I mentioned in a previous video, this is a very heavy vocab unit, and so pay attention to these following vocabulary terms as I cover them in the slides. Make sure you're doing your homework and memorizing these and getting on Quizlet and getting these down pat. So as we get started, you will need a calculator and a pencil and your notes because we will be doing some more practice problems. So temperature and heat. We already discussed in a previous video that temperature is actually a measurement of the kinetic energy. And we often think of heat as something we feel, which is still somewhat true. Heat is actually the transfer of energy. So when you feel warmth, energy is leaving something and coming into your body. And so remember, temperature is the kinetic energy measurement, while heat is an actual transfer of energy. The unit we're going to use for heat and energy is going to be joules, which is again labeled as a J. So as we remember what we talked about with our kinetic molecular theory, when we have more kinetic energy, we have a higher temperature, which is really because of the joules, the amount of energy in here that is transferring into the movement of the particles. So when we look at specific heat, we see that different materials transfer energy differently. Think of this between things that are good conductors versus things that are good insulator. A conductor can transfer energy relatively easy and quickly and efficiently. An insulator actually resists the change and resists the flow of energy. And so specific heat is actually a given amount. It's this value that has been researched by scientists, and you can find the specific heat on almost any substance in the world. But what it tells me is how much energy is required to raise the temperature of 1 gram of a substance 1 degree Celsius. So things like water, methane, glucose, everything out there that is used somewhat in society already has a studied, researched out specific heat, and this will have to be given to you when you do these kind of problems. But specific heat, again, is just the amount of energy needed to raise 1 gram of a substance 1 degree of temperature, which is typically in Celsius, but it can also be done in the unit of Kelvin. And so as we do this, and you see these equations below, you're going to see that mass also plays a role in the change of temperature. And so again, we're going to talk about enthalpy, which enthalpy is the basically energy of a system, but gives consideration to the amount of substance and the pressure of the substance. So here is the first equation we're going to deal with. This is, again, an energy equation. It's how we can calculate the heat change of a material. Now below, or in a few minutes, I'm also going to give you another equation. This equation is the amount of energy required to make a phase change. So this very, very simple equation, and there's actually two right here, is the equation we'll use in a moment to measure the amount of energy needed to turn water simply into gas or to turn ice simply into water. And so we take a certain amount of energy to change between the phases. But what this equation that we're working with first is actually tells me how much energy it needs to just raise the temperature or to lower the temperature. And so what we see here is that Q is actually our measurement of heat, the amount of energy being transferred. We're going to use this in joules. We see mass is in grams, something very familiar. C is my constant. This is going to be the specific heat. Notice the units on specific heat are joules per gram per degree Celsius, or it could also be written in joules per gram per Kelvin. And then TF and TI are final temperature and initial temperature. And again, these can be in degrees Celsius, degree Kelvin. It doesn't really matter. As long as you play nicely with your units, everything will work out nice and peasy. So again, this is a very simple equation to use. We're going to do some algebra, and then we're just going to plug and chug as we do some solving. So I want to give you a few practice problems here to practice and to watch how I do them. Again, like I've shown you with all algebra problems, when we look at this problem, identify the values, go through here and label everything that's given to you, and then do your algebra with the existing equation to solve for your unknown. So this first problem here, we can look at it and we can read it as what is the mass of water. So first of all, I see right off the bat it's asking me to solve for M, right? So if I'm looking at my equation we just got done dealing with, I'm going to use this equation and I'm going to solve for M. So I'm just going to go ahead and write it here for us. So that way it's nice and easy. Remember, TF minus TI, another way to write that is change in temperature. That change in T means exactly that. But again, it gives me the mass of water can be heated from 25 degrees Celsius. Again, that's going to be my TI to 50 degrees, which is TF, by the addition of 2,825 joules. This is going to be my Q when the specific heat of water is 4.18. Now, again, the units for that should have really been in joules per a gram Celsius, but got a little lazy writing the problem. But again, regardless, that is my C. So I see that I'm going to solve for M. So what I suggest you do is do your algebra early and then plug your numbers in. It will save you a lot of time. There's a lot less likely you're going to make a mistake. So if I want M by myself, I divide by C and change in T. You do it to one side, you have to do it to the other side. So simply to do this problem, I'm simply just going to take 2,825 joules. We're going to divide it by 4.18. Again, if I'm playing with my units, joules and degrees Celsius will go up here. My change in T would be the difference here, which is simply 25.0 degrees Celsius. Again, you can do that in your head. You can do it in a calculator. You can plug it in here however you feel comfortable. But that's just the difference. 50 minus 25 is all that means. And so then again, if I go and plug it into my calculator, it will come out to 27.0 grams of water. So again, what's the mass of water, 27 grams, that can be heated from 25 degrees Celsius to 50 degrees Celsius by adding 2,825 joules if this is the specific heat of water? Pretty simple. Next problem, if you're feeling confident and you've got your algebra, go ahead and pause the video, try it yourself. If you're not feeling confident, watch me do it, and I'll show you how to do it. Again, read through here. I see I'm looking for TF. They give me the mass. They give me the initial temperature, and it's giving me the Q. So if I see TF, I see TI, I see M, I see Q, I am missing C, which again, you can go back and pull it from this problem here. So now that I see that, I'm going to simply be solving for my TF. So again, what I suggest you do is do your algebra first, and this will make your life a lot easier because as you do it a few times, it becomes automatic, plus there's less likely to make a mistake when you go to plug your numbers in. So we're solving for TF. So the first thing I do is get MC to the other side. Now I see I got Q over MC equals TF minus TI. To get rid of TI, I'm going to add it. If you add to one side, you have to do the same to the other side. And so now I have my new equation, which I'm going to just go down here to the bottom and do. We're going to have TI plus Q divided by MC equals TF. Now simply go through there, add in your values. TI is 75 degrees Celsius. Q is 79,600. One thing to pay attention here is it says loses. So this needs to be a negative sign. And we're going to divide by my mass of 625 grams. And then we're also going to divide by 4.18. And that's joules per gram per degree Celsius. That's why all these units will cancel out and allow me to add this up nice and neat. And if you put that in your calculator, it is going to come out to 44.5 degrees Celsius. Now, just a reminder as you're doing this, you're going to want to put this in your calculator first to do the multiple division part first, and then go back and add your number at the end. But again, like I said, these equations are pretty straightforward. You're just going to use this equation, do a little algebra. So get in the habit of being able to recognize the values and their labels as you go through. So the next thing we're going to see here is that not only do we need the ability to calculate the amount of energy used in changing the temperature, but now we got to be able to calculate the amount of energy in a phase change. So basically what happens is when I go to boil water, I have to raise the temperature up to 212 degrees Fahrenheit or up to 100 degrees Celsius just to get the water ready to boil. And then to actually convert all that liquid water to gas water, I have to put tons more energy in there to make that phase change happen. And that's what these equations help you. These equations right here allow you to calculate how much energy it takes to actually convert a substance from one phase to another one. This right here, H of vaporization, is obviously the amount of, it's the constant. It's kind of like a specific heat, but it's the constant value that tells me how many joules per gram is needed to convert so much heat in the phase change of vapor. H of fusion, or heat of fusion, is actually an amount that, or is the constant we're going to use when it goes to come from converting from doing the phase change of a liquid to a solid. So again, these equations are pretty straightforward to use. You just simply take either this constant times the mass, or you take this constant times the mass, and it allows you to calculate the amount of energy to make a phase change occur. So here's a very straightforward equation, very straightforward question. Let me walk through it with you. And again, hopefully you're going to see how simple this kind of problem is. So in this situation, we're using this equation here. I'll put it up top for you so you can be reminded of what it is. So what is the amount of heat required? Again, amount of heat, that's our Q. It's going to be measured in joules. So again, I'm going to put my Q. What is it? To convert 25 grams, we're going to call that mass, from 0 degrees ice to 0 degrees water. Heat of fusion of water is 334 grams. So again, this value will have to be given to you. This is known as the heat of fusion. Again, this is just a value, a constant, that helps me determine how much energy it takes to convert every gram of water from ice to liquid. So simple equation here, you just take your 334 grams per joule, times it by your mass, 25 grams. And when you do that, it quite simply just comes out to 8,400 joules. So for me to convert ice to water, to go from solid to liquid, I need this much energy. Key idea here, simple equation, but just understand what we're doing. Here we're doing a phase change. So again, this is all about doing a phase change. And why I'm trying to point this out is because now on the next type of problem, we're actually going to apply both equations. So when I come to my third type of problem, what we're going to do here is we're going to actually use both equations. We're going to use the Q equals MC delta T, and we're going to use our Q equals fusion, heat of fusion, and we'll actually even use our Q heat of vaporization. And of course, these are both times mass. So as I read this problem, what we're going to see here is it's going to say, what is the heat in joules required to convert 25 grams of water from negative 10 degrees Celsius into 50 degrees of water? So what's going to happen here is I have to calculate the amount of energy just to raise it from negative 10 to 50, but then I have to go back and calculate the amount of energy needed to change the phase. So there's actually going to be three separate equations you're going to do here. We're going to use the QMC first, and we're going to use this to calculate the amount of energy needed to change from ice into water. Now down here, you're going to notice that the specific heat of water changes. When water is in solid form, it takes 2.09 mole or joules to convert every gram per degree Celsius. But once ice turns into water, the specific heat goes up in value. So therefore, this is why you're going to see us needing three equations. So the first equation we're going to use here is going to be this part right here when we're going from basically negative 10 degrees Celsius to 0 degrees Celsius, because that's when water is still in ice form, and I got to use this constant. So the first equation I want to use, the first form of heat I need to calculate, or energy, is going to be my 25 grams times my 2.09 joules per grams degrees Celsius times my change in temperature. And here I'm changing it 10 degrees. This is my initial, this is my final. So if I go 0 minus negative 10, that's why it's a positive 10 there. When I do that math, it's going to come out to 522.5 joules. Hopefully you guys can see that. I'm sorry. This next one now is I have to calculate the heat of fusion, the heat from the phase transfer. So now, once I went from 0 degrees to negative, or from negative 10 to 0 degrees, now I have to see, well, how much energy do I have to go to change it from ice, from solid, into liquid? And that's going to be using this equation, which again is just simply going to be your heat of fusion and then times the mass. That's going to come out to 8,350 joules. So you can see that it takes 522 joules to raise ice 10 degrees of temperature. It takes 8,350 joules to simply convert all that 25 grams of ice into liquid water. Now I need to find out, well, how much energy does it take to raise those 25 grams of water up to 50 degrees? And so we're going to use this equation again. It's going to be 25 grams. Multiply that by our constant. Here, we're doing a specific heat of water because now we're dealing with it when it's in the range of water. So it's going to be 4.18 joules grams degrees Celsius. And again, my temperature, my change in T is going to be 50 degrees. How did I come up with that? Because again, it's just simply my final temperature is going to be 50 degrees Celsius. My initial was 0 degrees Celsius. So that's simply 50. And when you do that math, it's going to come out to 5,225 joules. So you can see it takes an incredible amount of energy to simply convert just 25 grams of ice into water. And then it only takes 5,000 joules to raise those 25 grams of water up to 50 degrees. So to get my final question here, to find the total amount of energy to do all of this, I have to add these up together. And when you add them up together, you get a final value of 14,097.5 joules. You notice I am kind of ignoring sig figs here just because I don't want to focus on that while we're getting started. But if you were concerned about sig figs, you would go to that point right here. So how much energy? What is the heat transfer that is required to take negative 10 degree ice and to convert it into 50 degree water? You have to first calculate the amount of energy change in turning those 10 degrees of ice, get it up ready to transfer or phase change into water. Then you got to calculate how much energy needed to phase change it from ice to water. Then you have to calculate how much energy to raise that 0 degree water all the way up to 50 degree water. Add those together and get your answers. This might seem a little overwhelming right now, but I assure you that these equations will become very easy to you after we practice in class and see a few more examples. And so as we start to wrap it up, here's a long story short. Heat change in a substance differs based on the chemical properties of the substance. If I am looking at the specific heat of water, that is different than the specific heat of ice, which is different than the specific heat of gas. And all that is different from the specific heat of methane or glucose. And so the specific heats will always be given to you. Those things have already been researched out the wazoo, and you can always find that information through scientific websites or charts. The specific heat formula solves for the changes in heat when there is no phase change. So the first equation I gave you was how we can simply calculate the amount of energy change if there's no phase change. But then if we have to deal with a phase change, you have to use the phase change equations. And heat of fusion and heat of vaporization are required to calculate the change of heat during a phase change. And this was, again, just simply the second equation. So what we see is things had different specific heats. We see our first equation I taught you. We see the second equation I taught you. And like I said, I hope this really doesn't freak you out, because with a little practice, it should come pretty easy to you. Have a great day. In the heat